All right, so 6.3 is about exponential functions. We are going to identify exponential functions and determine whether they are growth or decay. Anybody need more time with the objective? All right, for our warm-ups, we are identifying the graphs as linear or absolute values. We've only got two options. We have graphed both of these types of lines before. It's been a while since we've seen absolute value ones. First one, Lydia, what is it? Very good. The first one is absolute value. What about the second one, Jasmine? Second one's linear. Number 3. Somebody else. Thank you, Dominic. Also linear. And the last one is absolute value. So remember, absolute value graphs make some sort of V, whether it's facing up or facing down, some sort of V. Linear is just one straight line. Questions, concerns about linear versus absolute value? Okay, when we talk about exponential functions today, it will look even different from either of those. So in our notes, an exponential function is a non-linear function of the form y equals a times b to the x. I'll write that a little bigger. Y equals a times b to the x power, where a is not equal to 0 and b is not equal to 1 and b is greater than 0. Those are just kind of technicalities. Okay, if a is equal to 0, then it's going to zero out whatever the b is. If b was equal to 1, 1 to any power is just 1, so then it would be constant. And b has to be greater than 0, meaning b is not going to be a negative. Right, the important part, I think even more important than all those qualifiers, is the idea of it being nonlinear. What does the word nonlinear mean to us? It what? Very good. Not a straight line. So nonlinear means it is not a straight line or not a straight path. As the independent variable x changes by a constant amount, the dependent variable y is multiplied by a constant factor, which means consecutive y values form a constant ratio. So when we were trying to identify linear functions, we were making sure that we were either adding or subtracting the same thing to y every time. This time y will instead be multiplied by something every time. Anybody need more time on this slide before we look at some examples? Okay. Does each table represent a linear or an exponential function? Explain. Okay. On especially 1, 2, and 3, it's important to notice that x is changing the same way every time. How is x changing? We're adding 1 to x. Okay, so x is constantly changing, especially on 1, 2, and 3. We'll talk about 4 a little separately. So then we go to our y values, and we see how the y values are changing. So here we were adding 1. How are the y values changing on example 1?
By 2.
What do you mean by 2?
Multiply by 2.
Every time?
Yes.
No, you add.
We're adding by 2 every time. Right? 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. Are we all okay with why that one's adding, not multiplying? Okay. So if we were adding to x every time and adding to y every time, do you think that's linear or exponential? Linear. Remember here we've got a constant rate of change. Your change in y over your change in x. So one way of saying that would be to say that there is a constant rate of change. Or you could say that you're adding the same value to y every time. Adding to y. Whereas exponential, we're looking for what operation? Instead of adding to y, we're looking for multiplying to y. All right, on example 2, again, we notice that our x's are adding 1 every time. That makes it a little easier. What's happening to the y values every time? We're multiplying by 2. So 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. So this one, do we think it's exponential or linear? Exponential. Why? Okay, because we were multiplying to y every time by the same thing. If we multiplied by 2, then multiplied by 3, then multiplied by 4, it wouldn't work. But we're multiplying by a constant factor. Constant factor. Okay, so we got to make sure we're multiplying y by the same thing every time. All right, on number 3, again, x is changing the same way, adding 1. We're more concerned about how the y's are changing as long as our x's are all changing the same way. What's happening to our y's on example 3? What is it? We're dividing by 2 every time. But is there another way we could think about dividing by 2?
Subtract.
Not subtracting. Dominic?
Multiply a half.
Very good. Instead of thinking about it as dividing by 2, you could think about it as multiplying by 1/2 or by 0.5. Lydia? What would your explanation be then? Okay, so that's why it's easier to show it as multiplication. You could show it as division, but you would have to word your explanation a little bit differently. So if you show it as multiplication, it's easier to say that this is what kind of function? Exponential, because multiplying y by a constant factor. There we go. Questions, concerns? Okay, so the notes just above these also mentioned at the very end there that consecutive y values form a constant ratio. So that means if you take a y value and the y value that came before it in a fraction, you should get your ratio. So here, 32 divided by 16, or 32 over 16 would reduce to 2. 16 over 8 as a ratio would reduce to 2. 8 over 4 would reduce to 2. Same thing at the bottom. 1 over 2 is a half. 2 over 4 is still a half. 4 over 8 is a half. That doesn't work on linear ones. On linear ones, if we look, 8 over 6 is not the same as 6 over 4 or as 4 over 2. They would not reduce to the same thing. Questions, concerns? Need more time? Okay, on number 4, how are the x's changing this time? The x's?
Subtract 4.
Adding 4 every time on the x's. So to get from negative 4 to 0, we would add 4. 0 to 4, we add 4. 4 to 8, we add 4. So the x's are changing the same way on this problem. It's not exactly the same as the other problems, but that's fine.
Subtract 1.
What's happening to the y's?
Subtract 1.
We're subtracting 1 every time. Minus 1, minus 1,
Linear.
minus 1. Why is it linear?
Because it's numbers.
Okay, we're not multiplying, so it can't be exponential. Another way of saying it would be that we've got a constant rate of change. Okay, so it would be negative 1 over 4th is our rate of change. Okay, if you were to put not multiplying y's on this one on a quiz or a test, I would accept that because that's what we were just talking about.
So
We weren't multiplying the y's.
does the negative affect it at all? Like,
Well-
does the negatives have a say-so over it? If it is negative, can it turn into exponential?
Can it turn exponential? I think that you could have negatives involved and it still be exponential. I don't know if we'll look at any like that, but I wouldn't say that the negatives alone make it linear. The fact that we're subtracting would make it linear. So if you were to just put not multiplying to get y's, that would be okay on this one. Now notice though that we were only given 2 options, either linear or exponential. Okay, so just because we aren't multiplying doesn't necessarily have to make something linear. Just want to point that out. It's not always necessarily going to be one or the other. It could be neither of them. Like an absolute value. Any other questions before we move on from our first set of examples? Okay. So we've seen what it looks like in a table. Next, we're going to see what it looks like in a graph. There are 2 types of exponential graphs, growth and decay. You can determine the type of graph based on the value of b in the equation y is equal to a times b to the x. So the b is what tells us whether or not it's going to be growth or decay. If b is greater than 1, then it's exponential growth. If b is less than 1, then it's exponential decay. This has nothing to do with the a value. So a could be positive or a could be negative, which is what you see here A is positive or greater than 0 on the top for both graphs. A is negative or less than 0 is the bottom one pointing down on both graphs. So, of course, for growth and decay, those words are probably pretty self-explanatory. If it's a growth, that means our y values keep getting bigger and bigger and bigger, one way or another, either positively or negatively, depending on what A is. For decay, our values keep getting smaller and smaller and smaller as we keep going. Growth and decay functions have a lot of applications as far as things like population growth or decrease, bacteria growth, things like interest on some sort of loan, or interest that you're earning on an investment. Lots of different possible applications for growth and decay. Questions, concerns about this slide? Ready to move on? Okay. Determine whether the following are growth or decay. Now remember that our generic function was y equals a times b to the x. And which of these letters did we say is important for identifying if it's growth or decay? B. And we know that it's b if it has an exponent on it. So a doesn't have an exponent other than a 1. B is what has our exponent of x. So b is what we're focusing on. So for number 5, do we think that's growth or decay? Let's see. Thumbs up for growth, thumbs down for decay. Thumbs sideways for we're not entirely sure how to decide. Seeing some thumbs up, some thumbs sideways. Some people don't have thumbs. Okay, so on the slide before, it said that if b is greater than 1, it was what? B greater than 1, it was growth. B less than 1, it is decay. So on number 5, what would you say b equals? What would you say b equals? Liam? 7. So, is b greater than 1 or less than 1? Greater, so it is growth. So this is how we will decide. Identify what b is, decide if it's bigger than 1 or smaller than 1, and that'll tell you whether it's growth or decay. So on number 6, what is our b? B is 1/2. Is that greater than 1 or less than 1? Less than 1, so this would be decay. Now on number 7, we see 2 numbers there. Which one is the b? 2/3. I know it's printed kind of small. B is 2/3. Is that greater than 1 or less than 1? Less than 1. So this is decay. On number 8, what is my b? 3. So this would be growth because it is greater than 1. Questions about deciding if it's growth or decay on 5 through 8? Okay, then we have to look at 9 and 10. When we look at these, do you think we're focusing on the x's or the y's? when we were deciding earlier if they were linear or exponential, which one did we spend more time talking about?
Why?
The y's. Y's are what tell you or help show you what's going on with the function. Your x's are changing the same way. What are we doing to the x's? Adding 1. That's not very exciting. Okay, x's should be changing some constant way, adding the same thing every time. Usually 1s, but we did see an example where we were adding 4 every time. The y's are what are more important to us. So how are the y's changing on example 9? I don't think so. 1 times 1 doesn't give me 2. A half times a half doesn't give me 1. I don't think we're adding the same thing every time. Okay, but that doesn't mean that we're adding a half every time or adding 1 every time. I'm going to tell you, this is exponential. This isn't linear, which means our y's should be what operation every time? Multiplying by something every time. So what are we multiplying them by every time? Dominic?
2.
Multiplying by 2 every time. A half times 2 is a whole. 1 times 2 is 2. 2 times 2 is 4. Okay, finding other patterns is all fine and dandy, but you need to know what you're multiplying by every time. Whatever you are multiplying by every time is your b. So in this case, b equals 2. So this is a growth function. Finding other patterns is nice, but we need to know what we're multiplying by every time in order to know if it's growth or decay. So on number 10, again, I will tell you we are multiplying our y values by something every time. What is it that we are multiplying the y value by every time? Liam? Nope, that would just make our numbers bigger, but switch them from negative to positive. What is it? Multiplying by 3? I think you're getting on the right track. However, we're not multiplying these each by 3 because our numbers are getting smaller. So yes, we're dividing by 3, but wording it with division isn't going to help me. Liam? There we go. Multiplying by 1/3 is what we're doing. Multiply by 1/3 every time. So anytime you want to say division, think about multiplying by the reciprocal. Do we remember doing that? Multiply by the reciprocal. So anytime you want to say divide by 3, think about it as multiplying by the reciprocal of 3, which would be 1/3. So this time my b is 1/3. So this is a decay function, which this should make sense even if we hadn't identified b. Our y values are getting smaller, so it's decaying, decreasing. Here our y values are getting bigger, so it's growing. Questions, concerns so far? Yes, ma'am.
Whatever we have to do with this, do you want us to put what the b is, or can we just put what it is?
If I want the b value explicitly stated, I will let you know. Otherwise, you can just give me an answer. Okay, if I ask for the b value, then for growth or decay, I need both. But if it just says growth or decay, you can go straight to your answer. Other questions? Okay. Last slide. Now on these ones, the B value, technically we could find. I don't know that I would require that. We could identify points and try to calculate our B value, but we should be able to just do this by looking at them. And you should always read your graphs from left to right. So from left to right, does it seem like our Y values are increasing or decreasing?
Decreasing.
Decreasing, so this we would call decay. So read your graphs from left to right. See what the Y value is doing. So same thing on number 12. Look at your graph from left to right. Is the Y value going up or going down? Going up, so this would be growth. Okay, we're keeping it pretty simple today, just identifying if it's exponential or not, and then if it is exponential, identifying growth or decay. Notice, though, that all of these exponential functions that we see in these two graphs or in the graphs on the top of the back of your notes inside that little box, these graphs don't necessarily look the same all the time. They have the same general features, meaning there's some sort of curve to it. It's not a straight path. But it's not like it's always a V or it's always a straight line. Okay, sometimes they'll curve really steeply, sometimes they don't curve quite as steep, but there is some sort of a curve to it. Notice, though, that it doesn't curve back around. There's only one curved piece. All things that you should be paying attention to.